Welcome again, ladies and gents, to another flipped lesson. Today, our focus is on these things called solubility curves. And what these solubility curves help us understand is that temperature not only helps us dissolve stuff faster, but it also impacts how much solute a solvent can hold. So that's going to be our main focus for today's video. So if we do a quick review of what solubility actually means. Remember, solubility tells us how much solute can dissolve in a given solvent at a temperature. So it tells us how many grams our liquid can hold at a specific temperature. Now your solubility, how much stuff can dissolve, is going to be impacted by these two factors down here. The first factor is the nature of the solute. And this goes down to the activity we talked about yesterday. That's looking at whether your solute is polar or nonpolar. Because remember, you only dissolve in stuff that's similar to you, because we have to follow the rule like dissolves like. So polar things can only dissolve in polar solvents, and nonpolar things can only dissolve in nonpolar solvents. So the type of solute that you are is going to impact how much will dissolve. The other thing is going to be the temperature. I love coffee. In the winter, I like it hot. In the summer, I like it cold. And I love to put a ton of sugar in it. But what I've noticed is that when I put my 2 packets of sugar in my hot coffee, it always dissolves. But in the summer, I always end up with sugar on the bottom of my iced coffee. And that's because we're going to learn that hot solvents typically hold a lot more than cold solvents do. So what we use to show that relationship is something called the solubility curve, which is this guy right here. So when we look at a solubility curve, what it does is it gives us 3 pieces of information. It shows us the amount of solute that can dissolve in a specific amount of solvent at a temperature. Now, the amount of solvent and the specific temperature are going to come from your axis labels. So the amount of solvent you're going to see on your y-axis, I'm going to label that with the number 1, and your temperature is going to be your x-axis. So if we look at this graph and we look at the y-axis label, this y-axis shows us the solubility. How many grams of solute can be held in 100 grams of water? So the solvent that we're using today is 100 grams of water. So what that tells me is all this data that was collected was based on how much of each of these solids will dissolve in 100 grams of water. So I was using 100 grams of water to get all this data. So that's how much solvent I was using. The temperature is going to be at the x-axis. And so what this temperature is going to do, if the line goes up, it shows us that there's more dissolving as the temperature increases. But if the line goes down, it means there's less dissolving as the temperature increases. Now, usually your solubility is going to go up as your temperature goes up. However, if you have a solute, like a gas, let's say, something like maybe carbon dioxide you're putting into soda, as the temperature of your liquid gets hotter, the solubility is actually going to go down. So this graph can show you, does it hold more as the temperature increases, or does it hold less as the temperature increases? And the amount of solute is going to come from the line itself, because all these lines that are on the graph are showing us where a perfect saturated solution exists. So for example, if we look at KNO3, if I was to make 2 solutions of KNO3 using 100 grams of water, one at 10 degrees Celsius and one at 40 degrees Celsius, for me to make a saturated solution, I have to put a different amount of salt into that water. So how you figure out what the perfect saturated solution is you look at your temperature and you follow it exactly up to the line. So that's where I hit my KNO3 line at 10 degrees Celsius. I follow it over to the y-axis, and what it tells me is at 10 degrees Celsius, my 100 grams of water can hold about 18 grams of KNO3. However, if I take that water and I heat it up to 40 degrees Celsius, my solubility gets way higher. At 40 degrees Celsius, I can hold about maybe 58, 59 grams of KNO3 in that same 100 grams of water. So you can see that for KNO3, as my as my temperature goes up, I can hold a lot more stuff in that same 100 grams of water. So if the lines show us saturated solutions, what we can do is we can use them also to figure out whether or not we have a saturated solution, an unsaturated solution, or a supersaturated solution. So let's go ahead and let's look at KCl for this example. If I look at KCl and I look at 70 degrees Celsius, let's say I only had 30 grams of KCl in my lab. So that would put me about here. So that would be how much KCl I would have dissolved in my 100 grams of water. But if I look at my solubility curve, I can see that KCl can hold over 40 grams. So since my amount is less than the line, that would mean my solution is unsaturated. So if you're given a data point that is below the line, it means that you have an unsaturated solution because you have room to add more solid to hit the line. So if you have less of your substance than the line tells you you can have, it would be an unsaturated solution. Now let's say I have that same 100 grams of water at 70 degrees Celsius, but I put in 70 grams of KCl. What that means is I have more KCl than my water can actually hold. So if I have more than my water can hold, that would mean I'm supersaturated. So if I'm above the line, that would equal a supersaturated solution. So with these solubility curves, you can use them to figure out, is your solution saturated, unsaturated, or supersaturated? If you fall exactly on the line, you're a saturated solution. If you're above the line, it means you're supersaturated. And if you're below the line, it means you're unsaturated. Now the other thing we can get from these graphs is we can get actual numerical representations of solubility. Now when we express solubility, it contains three parts. You have the amount of solute over the grams of solvent at a specific temperature. So if we were to look at the NaCl line from the previous slide, if we found 25 degrees Celsius, that 100 grams of water could hold 36.2 grams of sodium chloride. So we write it like a fraction. And we write it like this because it allows us to set up proportions that we can use to solve problems. Because as a chemist, I don't always need to make 100 gram samples of my solutions. Sometimes I need to make way more. Sometimes I need to make way less. So these proportions can help me figure out how much stuff I need to put into my solution to get that perfect saturation point. So let's go ahead and let's look at an example. So with solubility, the nice thing is we can use proportions to go ahead and solve problems like this. So for example, if I'm in the lab and I know I can make 5.2 grams of a substance dissolve in 16 grams of water, I can change it to figure out how much that would be in 100 grams of water using a proportion. So I would take what I know, which is my 5.2 grams of my solute dissolves in 16 grams of my solvent, and I'd set it equal to x over 100. And I solve by cross multiplying. So I'd end up with 16x equals 520, and I would have x equals, when I punch that in my calculator, dividing by 16, 33. So what that tells me is my solubility is 33 grams per 100 grams of water. So that's one thing we can do. The other thing we can do is we can look at different problems looking at solubility curves. So let's go back to what we were just trying on the previous page. So if we had a question like what substance has the highest solubility at 50 degrees Celsius, and here's our options, what we would do is we want, okay, the highest solubility, let's look at where each of these things fall at 50 degrees. So here's 50 degrees. My HCl is right here. So now we're going to compare everything else to that. So if I look at NaNO3, my NaNO3 is way up here. So I know it can't be my HCl. My SO2 is way down here, so I know it can't be that. And my NaCl is right here, so it can't be that. So I know my answer is B, NaNO3. What I'd like you guys to do right now is I'd like you to try numbers 3 and 4. So go ahead and hit pause on your note sheet, hit 3 and 4, and I'll come back and I will help you get those answers. So I'm assuming that you guys now have finished numbers 3 and 4. So let's go ahead and let's look at the answers to those problems. Which substance has the lowest solubility at 50 degrees? We're going to do the same thing that we did before. So we look at HCl, which is right here. Our NaNO3 is way higher, so it can't be that. Our SO2 is way lower, so it can't be HCl. And NaCl is all the way up here. So our answer with the lowest solubility is going to be SO2. At number 4, how many grams of HCl can dissolve in 100 grams of water at 25 degrees Celsius? So let's go ahead and let's find 25. And how you answer this is you follow it up to the line. So I'm at 25 degrees Celsius. I follow it till I hit my HCl line, which is this guy right here. Then I follow that over to the x-axis, and I see that it is 70 grams of HCl in 100 grams of water at 25 degrees Celsius. Our last question here, I've got 40 grams of KCl completely dissolved in 100 grams of water at 80 degrees Celsius. This solution is, how we tackle this one is go, okay, I'm at 80 degrees Celsius. I've got 40 grams, which would put me right here. So let's find our KCl line. Our KCl line is this guy up here. So since I'm below that, I would be an unsaturated solution. 5b, how many more grams of KCl can I dissolve? So again, I'm looking at that same line. I'm at 80 degrees. I had 40 grams. My KCl line is right about 50 at 80 degrees. So I could hold approximately 10 more grams in that 80 degrees Celsius water. On your note packet, you guys have 2 more questions that are a little bit of a tweak on what we've learned today. And I'd like you guys to try and fill out those on your Google form. They're questions 6 and 7. And I'll be starting class by explaining those tomorrow. Remember, if you have any questions, you could always email. Have a great night, guys.